Assalamu alaikum guys. Today we are going to start our next topic, pressure and its measurements. What is pressure? Fluid will exert a force normal to a solid boundary or any plane drawn through the fluid. Since problems may involve the bodies of the fluids of indefinite extent, and in many cases the magnitude of the force exerted on a small area of the boundary or the plane may vary from place to place, it is convenient to work in terms of the pressure P of the fluid, defined as the force exerted per unit area. If the force exerted on each unit area of the boundary is same, the pressure is said to be uniform. For the uniform pressure, the equation can be developed as the pressure is the force that is acting or exerting on a unit area of the boundary. Force divided by the area. Or in terms of notations, it will be P is equal to F over A. This is the very simple and the basic definition of the pressure that is held going to be hold true for any type of the body, that may be the solid or the fluid. We are talking about specifically for the fluids. So for the fluids, if the pressure is going to give you the same value on each unit area of the boundary in which our fluid is resting or keeping, so we are going to be say that pressure is uniform. And for the uniform pressure, we are not going to be considering any differential element, and we are not integrating it, or we are not going to be considering any other terminologies or any other technique to solve it out. Directly, the pressures in terms of the forces and the unit area, we can take the notations and we can input the values. For the fluids, usually the uniform pressure doesn't hold true, and sometimes it is going to give you a variation once it is flowing or even it is at rest. So, if it is more commonly the case of the pressure in which it is the pressure changes from point to point, we consider the element of the force that is differential F, delta F normal to a small area delta A surrounding the point under consideration. Your mean pressure for any differential element now will be the small p is equal to delta F over delta A. Now, what this differential element is? This differential element is going to give you the case in which we are going to be observe the pressure that is exerting on within a boundary that is changes from point to point. If it is not uniform, like the previous case, that it is not same throughout the boundary, it is going to give you some variation, some changes within the same boundary from point to point. Then you need to be considered a differential element. For this differential element, the forces that is going to be acting on the differential element having a certain area that will be very small, and the forces acting on this differential element will also be very small. So you are going to be consider these differential forces and the different that is acting on a differential area that is going to give you the pressure. And actually this is going to be called as the mean pressure, in which you are going to be adding up all the forces or the pressure acting on each differential element, and then finally you are taking mean of it, and it is going to give you the pressure. Now once the mean pressure is with you, in the limit as differential area delta A approaches to 0 but remains large enough to preserve the concepts of the fluid as a continuum, you can calculate the pressure at a point. In this way, you need to apply the limit. Your delta A that approach to 0, delta F over delta A, then you are going to be obtaining at the end dF over dA. That is going to give you the units in newtons per square meter, in which the alternate units you are going to be using for the pressure, that is bar, that is 10 raised to power 5 Newton per meter square. You must be familiar with this bar unit. Sometimes we are going to be measuring our pressures in terms of Newton per meter square, and sometimes we are measuring our pressures in terms of bar. If we are measuring our pressures in terms of bar, then it will be 10 raised to power 5 Newton per meter square, and its dimensions will be ml minus 1 t minus 2, that is the same as of the pressure. Now we will discuss about the Pascal's law. This Pascal law states that the pressure at a point in a static fluid is equal in all the directions. This statement is very important if we want to determine the pressure of any point within the fluid having a certain density. Just to drive this statement, we need, or justify this statement, we need to consider the equilibrium of a small fluid element in the form of a triangular prism, as shown in the figure, that is surrounding a point in a fluid. Here you can see this triangular region. If this is the point, any point P that is on which that point we need to determine the pressure, hydrostatic pressure. So if we are required to determine the hydrostatic pressure for this particular point, then we need to be consider surrounding to this point a triangular region. This triangular region that we can see in the front face, that is in the two-dimensional. If we are going to be adding in the lateral direction, the thickness of this triangular region, that is going to give you a triangular prism having a certain thickness delta Z. And this prism is going to give you an inclined dimension, that is delta S. If we talk about the dimensions, then the delta X will be the base of this triangular prism. Delta Y will be the height or perpendicular for this triangular prism. And delta Z will be the thickness of this prism in the lateral direction, and delta S will be the inclined dimension for this inclined face. Now the next is the applied forces on this isolated region around, that is surrounding that point on which we are interested to determine the pressure. A relationship can be established between the pressure Px in the direction, in the x direction, Py in the y direction, and Ps is normal to any plane inclined at any angle theta to the horizontal at this point. Three forces we are going to be considered over here. The first force is the Px, that is going to be acting in the phase, that is A, B, E and F. A, B, E, F is the plane normal to which you can see this force Px has been applied. So if we are going to be highlight this region or this plane, then we can see this is the plane. Okay, so this is the plane normal to that. Your force in the horizontal direction, in the x direction, you can see the direction of the x's just at the right top of your slide, that x direction is in the right direction, y is upward and z in the lateral direction. So in the x direction you can see the dimension is delta z, and in the y direction your dimension is delta y, and your Px is the force that is going to be applied in the horizontal direction normal to that plane, that is having the dimension delta y and delta z, and this plane is A, B, E and F. Second force that is going to be applying on this system, it is in the y direction and it is called as Py, and it is towards the system, towards this differential element. This differential element, because the force is going to be applied on this fluid differential element from the surrounding, and from the surrounding this is in the y direction. So Py is exerting on the plane that is at the bottom of this triangular prism. If we are going to be highlighting it, then this bottom face, this surface or this plane is the plane normal to which this Py force is going to be applied. This pressure is, or in terms of pressure, has been applied. Okay, so now if the forces are there, then how you can define the dimensions of this plane? This is delta x into delta z. This is the plane normal to which the Py has been applied. Now Ps is normal to any plane inclined at an angle theta to the horizontal at this point. So this is the surface, this is the inclined surface, that is A, B, C and D, normal to which this Ps has been applied. These pressure forces has been applied. Okay, so these are going to be produce you the pressure on the inclined surface. Now the forces acting on the elements, you can broadly categorize the forces in terms of pressure. Those are going to be exerting a pressure on this triangular prism differential element, those are two categories. The first category is the pressure forces normal to the surfaces, and we have discussed about these three normal forces, those are acting on this triangular prism differential element. The second one category of the forces is the weight of the element in the vertical direction. So your weight is always acting downward. You are familiar with that. So if this fluid is having a certain density, then what you can do, you can just show your weight of this element, differential element, that is acting downward. Okay, with this fluid is having a certain density, a certain weight, and according to that, this density,
now continuing with the Pascal's law,
applied downward.
we have discussed
so if we are going to be define the center of this fluid is at rest, and we are going to be draw a perpendicular,
px will act at right angle to the plane AB,
weight of this element,
py at right angles to CD,
these forces,
and ps at right angles to ABCD.
Since the fluid is at rest, there will be no shearing forces on the faces of the element. That will be our first assumption, or the basic assumptions to drive the Pascal's law, that your fluid will be at rest. No shearing forces are going to be developed within it, and the element will not be accelerating. So the sum of the forces in any direction must therefore be zero. The summation of the forces in all the directions must be equal to zero, meaning in a particular direction. So if we are going to be consider all of two directions x and y one by one, then first of all considering the x direction. If we consider the x direction, then first of all the force that is actually normal forces, that is those are actually acting on this triangular prism element, differential element in the x direction. This will be px, due to the px pressure due to the forces acting in the x direction. So this will be px into the area ABFE, this particular phase that we have discussed in the previous slide. So the area of the on which, or the surface plane at normal to which this force in x direction has been applied, this is equal to delta y into delta z. Second force that is applying in the x direction will be the component of the force Ps due to the pressure Ps that is exerting on the inclined plane. So the force or the pressure that is exerting on the inclined plane of this differential element, that is going to be having two components, one along the x direction, second along the y direction. So if we are considering the forces in the x direction, then the component of this force in the x direction we need to be considered also. So this is going to give you first of all the force multiplied by the area, and then its component by multiplying it with the sine of theta. And finally you are getting, by inputting the values in the dimension forms, you are getting ps into delta y into delta z, and this direction of this component of ps in x direction will be in the negative x direction, so minus sign will be there. As py has no component in the x direction, the element will be in equilibrium if. Now py is applying in the y direction, so this force, normal force, we are going to be considering in the equilibrium conditions for the forces along y-axis. So here only the x directional forces are needed to be considered. So for that only two forces are applying on this differential element along x direction. That will be the px delta y into delta z, this first one, okay, and the second one minus ps delta y and delta z, the component of the ps in x direction. Now if we are going to be simplify this equation, we will get px is equal to ps. Keep this equation with now. In the next slide we can consider the y directional forces. So forces due to py will be simply the force multiplied by the area of that plane or that surface normal to which this force has been applied. So this area will be the area of CDEF plane, and in dimensional terminologies it will be delta x and delta z. Second is the component of the force due to ps. It will be minus ps into the area normal to which this ps has been applied, and cos of theta is to considering its vertical component in the y direction. So weight of the element will be equal to minus specific weight into volume, and the third component along the y direction will be the weight of the element, as I have told you. So this weight of the element can be calculated by multiplying the specific weight with the volume of this element. This volume of the element you can calculate by considering the area of the triangle in 2D case, in dimensional phase, and multiplying it with the thickness in the lateral direction. So if this is the case, the total volume can be calculated, and rho g is simply the specific weight of this fluid element, differential element.
So as px has no component in the y direction, so in the y direction the three forces we can consider to develop the equilibrium conditions for this particular element. So first force is the py delta x delta z, you can write over here. Second one is minus ps delta x delta z, that is caused by the vertical component of the normal force applied on the normal plane. So here this term is added over here, and then finally the weight of the element, that is added over here. And if you need to simplify this equation in the next slide. So after simplifying the previous equation, you will get Py is equal to Ps. So if we are going to be considering last two equations, then we will see that our Ps on one side is equal to Px, and from the other equation it will be equal to Py. So Ps is equal to Px and is equal to Py. Mean the forces, pressure forces, the pressure that is exerting normal to the plane of the prismatic, triangular region, triangular prism, that is normal, horizontal and vertical, all are the same. So we can justify now the statement of the Pascal law that the pressure at a point in a fluid, static fluid, is same in all the directions. So this is known as Pascal law and applies to a fluid at rest. If the fluid is flowing, the shear stresses will be set up as a result of the relative motion between the particles of the fluid. The pressure at a point is then considered to be the mean of the normal forces per unit area on three mutually perpendicular planes. Since these normal stresses are usually large compared with the shear stresses, it is generally assumed that Pascal law still applies.
Now, if the pressure is give you a certain variations, next topic is the pressure variation in a fluid at rest. If this is the particular case, you need to be consider a fluid element of dimension delta x, delta y, and delta z, a cube element, and surrounded by the same fluid of the mass having a density rho. You need to suppose that the pressure is P at the center of the element. The forces acting on the element are the body forces like the self weight and the surface forces transmitted from the surrounding fluid. Since the fluid is at rest, the elements must be in equilibrium and sum of all the vertical forces must be zero. And the pressure on the opposite vertical faces must be equal. Thus, delta P over delta x should be equal to delta P over delta y, and this should be equal to 0. What does it means? It is not going to give you a different answer. Just we talk about the or we are going to be including the heights of the fluids, okay, in the x direction, in the y direction, and in the z direction. In this particular case, we are having now the axis system like this, in which the horizontal axis is x and the vertical is z, and the in plane dimension or axis is y. Okay, so if we talk about the two dimension or in plane dimensions, these will be delta x and delta z. And now if we talk about the perpendicular or transverse direction, that will be delta y inside the plane. Okay, so I mean thickness of the fluid element. This fluid element we are isolating from the whole fluid or the complete fluid in this way, that is going to exerting a pressure from all the directions. So this will be equal, we have concluded from the Pascal law. Now what we are going to be discussing over here, that if the pressure exerting, that is going to give you the rate of change of the pressure with respect to the rate of change of dimension in this particular in the particular direction, that will be equal to the rate of change of pressure in with respect to the dimension in the other direction, with the respective direction, you can say. So if the respective dimensions are going to give you the rate of change with respect to the pressure same, then you are getting the zero answer, and it will be the same. Rate of change of pressure with respect to a certain dimension and the rate of change of pressure with respect to a certain dimension in the other dimension, okay, that will be equal to 0 if we want to be in equilibrium conditions. So we will going to be prove that if you are going to be taking sigma fz is equal to 0, mean in the vertical direction, only one direction is enough, because this is very important direction in which the weight of the fluid is also including. In the x direction, usually we can consider it also. It is going to give you the same answer, same result, but preferably we are going to be considering the y direction because it is going to be including the weight also. Okay, and we can also relate our weights with respect to the gamma specific density with respect to the pressures, and we can just give you some relationship of those. So for to generate this relationship, we can have the all of the forces, the sum of all of the forces along the z direction should be equal to 0. If this is the particular case, then you can write the equations for the forces acting in the y direction. For the surface forces, these are the surface forces for the top surface and for the bottom surface. In the y direction, if we talk about, then two forces are going to be acting on this differential element, that is we are isolating from the surrounding, from the top surface and from the bottom surface. Okay, so if we consider this top surface, then this will be equal to the pressure that is exerting in the center of this fluid element, that is P. So at the top, this P is adding the certain pressure that is exerting on the top surface. So this element is, or this pressure is delta P over delta Z, delta into delta Z over 2 half of it. Okay, and this delta X and delta Y is the forces. So if we are to talk about the differential element, so this is the differential change in the pressure, that is from the midpoint of this element till the top surface. If we talk about, so P is the pressure that is exerting at the center of this fluid element, and if we come up from the center till the top surface, this particular upper surface, so in between the change of the pressure can be added into the pressure that is exerting at the center of the element, that is an additional differential or the change of the pressure that can be calculated in this way. Okay, so delta x into delta y is simply the area of this plane on which, or normal to which, this force is acting, this pressure is acting. Okay, so in this way this force can be calculated for the top surface. Now if we talk about the bottom surface, then if the pressure exerting the center point is the P, then it is the at the bottom level, so we can minus it, subtract it. The change of the pressure is subtracting if we come from center till the bottom, so this is in the opposite direction. So for this case, you are subtracting the differential change in the pressure from center till the bottom surface. So it is going to give you this value, and delta x into delta y is the same area, okay, of this plane on which, normal to which, this pressure is exerting. So in this way you are calculating, you can input the equation for the force that is exerting on the bottom surface and at the top surface of this element. So the rest is the weight of this element. This weight is acting downward actually, and the point of application of this force, this weight forces, is it is again in the center. So in this way we have the specific gravity, mean gamma, multiplied by the volume of this fluid element. So this volume is delta x, delta y and delta z, and gamma is the specific weight. So if we are going to be simplify this equation, we are getting delta p over delta z is equal to minus gamma. All of the things are going to be cancelling out or just getting be 0. So we are having, and if we are applying the limit for this equation from the differential, we can come to the d, the rate of change of the pressure with respect to the dimension in the z direction, rate of change of the dimension in the z direction, that will be equal to minus gamma. So how we can conclude this equation, and we can just write the explanation for this final conclusion, that is, in any fluid under gravitational attraction, pressure decreases with increase of the height z. If the vertical height of the fluid having a certain density rho, or means specific gravity gamma, if this is the specific weight gamma, if this is the height of the fluid element, you can say, or the total fluid, you can say. So for this particular case, if the gravitational attraction exists, for that particular case your pressure decreases with the increase of the height. So this is going to give you the inverse relationship. If the height of the fluid is going to be increased, then the pressure is going to be decreased. So in this way we can conclude this relationship of the fluid mean for the case in which the fluid is surrounded by the fluid element is surrounding by the fluid with the same density. In this particular case, you are going to have this equation dp over dz is equal to minus gamma, in which your pressure is going to be decreased with the increase in the height z in the vertical direction. So if we talk about for the fluid now practical example, if we talk about, so we need to be considered first of all a fluid at rest, secondly the fluid of the constant density. If this is the particular case, then gamma can be replaced from the previous relationship in the previous slide that we have discussed. There we can just replace our gamma with rho g, with dp over dz the same value. This can be integrated immediately to give the value of the pressure for the whole of the fluid. If certain container is with us and in which the fluid is resting in this container at atmospheric pressure, having a certain density rho. If we talk about any point in the fluid at which we want to determine the pressure, then that point must be having a certain height from the datum point or from the surface point, okay, below the datum or below the top surface. If from the top surface of this fluid this height of that particular point, mean the depth of that particular point will be equal to h in the vertical direction, then we can find out the pressure pressure exerted on this point that is having a location that is having a location at x. This x point, the pressure at x point can be determined. Okay, so for this particular case you can integrate now this equation to get the actual pressure, the whole pressure. So this pressure can be calculated. If you are going to be integrating it, it will be equal to minus rho g into z and plus constant of integration. So in a liquid, the pressure P at any depth z measured downward from the surface, so that z is equal to minus h will be. Now in this particular case, your z and this equation will be in the minus direction. Okay, so this is inside the fluid in the bottom direction. So you are moving, if you are going to be considering the surface of the fluid as a datum point. So actually your point x at which you want to determine the pressure exerted, so this is just at below the datum point. So for the point that is below to the datum, we are going to be considering this height as negative. So this negative height is going to be cancelled out with the negative that is already present in the equation, and you are getting rho g h and plus constant. Since the pressure at the free surface will normally be the atmospheric pressure, okay, so that constant can be replaced with the atmospheric pressure. And this atmospheric pressure is considered further, generally we are considering this atmospheric pressure as a datum point. So if this we are considering as a datum point, so we are starting from the zero or absolute point, so we can just remove it, and we are left only with the rho g h on the right hand side of the equation. So it's very convenient that you are going to be consider the atmospheric pressure as the datum. Okay, if you are going to be measuring the pressure measured above the atmospheric pressure is known as the gauge pressures, and we are going to be discuss in the coming slides about the gauge pressure, that what is it. So finally you can have the equation for to determine the hydrostatic pressure, that will be equal to rho g h. So this hydrostatic law states that the rate of increase of the pressure in a vertical direction is equal to the weight density of the fluid at that point. So if P over H, this H if you are coming on the left hand side of the equation, so P over H. So this ratio of P over H will be equal to gamma. That will be the same as we have discussed in the previous slide. Okay, so P is equal to rho GH, or P over H is equal to gamma. That is the alternative ways to write the equation for the hydrostatic law or to calculate the hydrostatic pressures. Okay, so this law states that the rate of increase of the pressure in a vertical direction, this vertical direction is very important, this is actually Z, or in this case it is H. Okay, so it is equal to the weight density of the fluid. So if you are going to be having whatever the weight density, mean this rho density or the gamma value is there, that is directly having a relationship with the rate of change of pressure with respect to the height. If you are going to be increase the height, then pressure is also going to be increased. So pressure head can be calculated H, if in other terms, if pressure is only you are interested in pressure, then you need to consider the previous slide. If the pressure head, mean this height of the fluid at which the certain pressure can be developed is needed to be determined, this pressure head will be equal to P over rho g, and that you can derive from the same equation that we have studied in the last or in the previous slide. H will be equal to P over rho g. In fluid statics or in hydrostatic pressure terminologies, in this way, this small h, that is the height of the fluid at which the pressure is needed to be determined, required to be determined, that certain height is called as head of the fluid. Or in other terms, we can say it is pressure head of the fluid. Sometimes we are saying it as a pressure head, sometimes we are saying it as just head of the fluid. Okay, so this pressure head is very important in certain for the during the analysis of the fluid at rest, and once we are measuring the pressures of the fluid, there in terms of the pressure head it also required to determine the parameter. This parameter is very important. A pressure of there is one very standard values we are discussing over here, that a pressure of 100 kilonewton per meter square can be expressed in terms of the water having a density, we know that 10 is to power 3 kg per meter cube, as a head of, if we are needed to be determined the head, okay, for the pressure 100 kilonewton per meter square. So we are inputting the values for the particular or the specific pressure at which the head is needed to be determined. So this pressure needed to be generated 100 kilonewton per meter square. For the water, its density is, for the water we are talking about, fluid is water over here, its density is standard and G is also 9.81. So it head should be 10.19 meter of water. So in this way, if for a certain system the pressure is required, hydrostatic pressure is required to be generated for a particular system, have to for a certain known values like 100 kilonewton per meter square, 200 kilonewton per meter square, for that, if the water the fluid is water, then we can determine the pressure head, that the head should be this one to develop a certain pressure, specific pressure. So if we talk about the other fluids, so we need certain relative density. In terms of the mercury, let's suppose, then first of all this rho needed to be converted into by multiplying it with the relative density of the mercury, that is 13.6, and with this to develop the same pressure 100 kilonewton per meter square for the other type of the fluids, that is other than the water like mercury, that will correspond to a head of 100 into 10 is to power 3. We are multiplying the rho with the relative density 13.6, and you are multiplying it with the G 9.81. This head should be, or the pressure head should be 0.75 meter of the mercury. So fluid to fluid, it is going to be varied. The pressure head is going to be varied. So what is going to be dependent factor now? The dependent factor will be the density. To develop the same pressure for the different fluids, if the density is different for the different type of the fluids, then the pressure head developed for this particular type of the fluid will be different. Okay, so this is the conclusion that we have till now we have made and we are discussing. Now another system be there, if you have the same container and at the different points the pressure heads or the pressures are needed to be determined. So if how you can equate, okay, equality of the pressure at same levels in a static fluid. If in the static fluid be there in which a certain type or the different way, mean to say the points be there in a horizontal direction, this point P, first of all we need to determine the pressure P1 at acting on point P, and on the other side we need to determine the pressure of this point, particular point Q, that is P2. So whether these two values of the pressures developed on these 2 points P and Q will be same or the different. If there is no height difference, you can see any point you can take as datum. Let's suppose this bottom surface you are considering, or the top surface you are considering as a datum for the height of this point P and point Q. If the height is same and the fluid for the point P and point Q is same with the same density, density is not going to be varied, then the pressure developed at point P will be equal to the pressure developed at point Q. P1 will be equal to P2. Similarly, if this is the particular system in which you are needed to be calculate the pressure at point P, at point R, at point Q, at point S, with a certain vertical distance, that may be Z or H, anyone. Here in this equation it is Z. Okay, so any Z distance be there. If we are going to be consider the P and Q as in datum, let's suppose, so we can say that your pressure exerting on the point R will be equal to the pressure exerting, hydrostatic pressure exerting at point S. PR will be equal to PS. So how to calculate the PR? Your PR will be equal to the pressure exerting at point P plus this height. Okay, mean the pressure head of between the point P and PR. Whatever the pressure is at P, this will be P pressure at P, and at the point P. You are adding the additional pressure that is due to the head developed between P and R. And this head is developed due to this height, that is Z. And this pressure head will be equal to rho GZ. Okay, and this will be the same for the other point also. So in this way, your PR will be equal to PP plus rho GZ, and same. If you are going to be equating both, you are cancelling out this factor and you will be left with PQ and PR. So whatever the pressure exerting at PR will be equal to PS, because those are at the same height, and your P pressure developed at point P will be equal to pressure developed at point Q, because both are at the same levels. So this level is very important within a container in which your fluid is resting, or your fluid is at rest, for the static fluid specifically. So for that, if the level of any 2 points or 3 points or 4 points is same, then the pressure head developed on these two in all the points will be the same. So the similar kind of the results we can also explain in another way, in which we can say that this is a hydrostatic paradox. Mean to say that if the weight of the fluid is different but giving you the same height and the base area, if the different type of the fluids or different vessels of in which you are inputting or keeping your fluid at rest, okay, so weight, if let's suppose is different, but the density is same and the base area is same, and this height of the fluid means Z or H will be the same from the top surface at any datum point till the base at which you are needed to be calculate the pressures at the bottom. Okay, let's suppose. So if in this case all of these systems you can see, the first one, the second one, the third one, and fourth one will give you the same pressure heads or same pressures at the bottom. In this way, keeping the density same. Okay, so the pressure on the bottom in each cases will be the same. Although the weight of the fluid is obviously different in four of the cases, the force on the basis of the vessel is the same depending upon the depth H in the base area A. So finally you can say that the point at which, mean the level at which you want to determine the pressure head or any pressure, hydrostatic pressure, if the area of this particular point is same, I mean base area, let's suppose it's bottom, then the base area, if anywhere in between you want to determine, if this area is same, let's suppose if you want to determine the pressure at this particular point, if this particular point, you will see, let's suppose we are just marking a level for these four systems. Now if you will ask to determine the pressure at this particular point, okay, for all of these vessels or these systems, so what is the case? Now the value will be different, because here from starting from the datum point, this will be H, although the height will be the same for all these cases, but your base area is different. Here base area is this one, here base area is this one, here base area is this one, here is this one. Okay, so this area for all of these four systems is different. So your pressure will be different. Okay, but for this particular case here at the bottom, you can see this area, this area, this area, this area, this bottom area is same. So at that particular point, if you want to determine the pressure, so this base area multiplied by the vertical height will remain same. But anywhere in between, or you want to anywhere in between you want to determine the pressure. Now, keeping the same lines, the next topic is to discuss about the absolute and the gauge pressure. Here in this graph, if we are going to be talk about the different terminologies, you can see here we talk about any pressure that is going to be called as the absolute zero pressure. If we come up very slowly or gradually, we are increasing our pressure from the absolute zero, then let's suppose we are at a certain point, that is the atmospheric pressure. Another point we can mark in which we talk about the atmospheric pressure. Between the atmospheric pressure and the absolute zero, what type of the variations we can get? We can get a certain pressure of the fluid that may be more, or the certain fluids we can have that is going to give you the pressures more than the atmospheric pressure, and certain fluids may have the pressures less than the atmospheric pressure. Now, one by one, we will discuss all of these cases in which, first of all, the fluids are having the absolute zero, mean absolute pressures, and having the atmospheric pressure, more than atmospheric pressure, and less than atmospheric pressure. If the pressure is measured relative to the absolute zero, your datum point is absolute zero, it is called as absolute pressure. Okay, like this. If you are here, your fluid is this one, this uppermost line is the fluid under consideration, and you are considering to calculate or to measure the pressure of this particular fluid with respect to the absolute zero, then this is going to be called as absolute pressure. The datum point is now for your fluid under consideration is the absolute zero, not the atmospheric pressure or any other pressure. If the absolute zero is the datum point, okay, with the reference to this, you are calculating the your pressure of the fluid, then this particular pressure you have measured is called as absolute pressure. If the pressure of the fluid is measured relative to atmospheric pressure as a base or as a datum, it is called as gauge pressure. Now, if we come up and atmospheric pressure is considered as the datum point, the base point, and you are having the same fluid, this top line, I mean that fluid is under consideration for which you want to determine the pressure. If you are going to measure the pressure of this particular fluid, now relative to the atmospheric pressure, considering the atmospheric pressure as a datum line, then this pressure is going to be called as gauge pressure. Okay? If the pressure is below that of atmosphere, it is designated as a vacuum pressure. Now two cases be there. After this, if the datum point is or the reference point is absolute zero, then only one condition, you are getting the absolute pressure. There is no other case. But for the second case in which we are considering the atmospheric pressure as a reference line, as a baseline, as a datum point, datum line, then we may have the two cases. A certain fluids may have the pressure more than the atmospheric pressure. Certain fluids may have the pressure less than the atmospheric pressure. If the pressure is more than the atmospheric pressure, it will be the gauge pressure. If the pressure is below the atmospheric pressure for the fluids under consideration, then it is going to be called as vacuum or the negative gauge pressure. Vacuum pressure or negative gauge pressure. And its gauge value is the amount by which it is below that of atmospheric pressure. A perfect vacuum corresponds to the absolute zero pressure. So, if we want to measure the perfect vacuum or perfect pressure, then the datum should be reverse of that. You are not going to be, for sometimes we are considering the datum point as atmospheric pressure for the gauge pressure, and sometimes we are considering it as at absolute zero. And from the absolute zero, considering if we are considering the reference point or the datum point absolute 0 to calculate the gauge pressure, it will be the absolute pressure again. Okay, so sometimes we can calculate our vacuum pressure in terms of absolute pressure, and sometimes in terms of the negative gauge pressure that is considered from the atmospheric pressure. So we can come down from the atmospheric pressure, and on the other side we can come up from the absolute pressure. Okay, so it will be positive in this particular case, and in this particular case it will be negative. You must show the negative sign if the datum point is atmospheric pressure for the gauge pressure. If for the gauge pressure you are considering the datum line as absolute 0, and from the absolute 0 you are measuring your pressures, gauge pressures or the vacuums, then it will be positive. That is very important. So whatever the measuring device you are using to measure the pressure, or for the vacuum, you must be clear with that. Either this device is using the absolute pressure as reference or the atmospheric pressure, and then correspondingly you need to consider the negative or the positive point. Okay, so in this way P absolute will be equal to P atmospheric plus P gauge. Now this is the thing, if the absolute pressure is needed to be calculated, if we are considering it from the datum point as considering as absolute 0, then you can further classify or just divide it into two parts. Okay, considering this atmospheric pressure as an intermediate, or you can say the any intermediate point. So further it can be divided into two parts. Absolute pressure, the whole pressure, absolute pressure will be equal to the sum of the P atmospheric plus P gauge, this upper point. Okay, so starting from the absolute 0 till the atmospheric pressure, it will be P atmospheric, this first term, and then from here till top, mean this fluid is under consideration, so this is the gauge pressure for the fluids in which the pressure is more than the atmospheric pressure. For the cases in which the P vacuum is needed to be calculated, then you must be come down, mean you need to subtract the P atmospheric from the P atmospheric, the P absolute values. Okay, so if this ordinate is needed to be calculated, this mean the vacuum pressure is needed to be calculated, then P atmospheric is the total ordinate, and from this ordinate you need to subtract this absolute pressure that is measured from the datum, considering the datum point as absolute 0 till the pressure of the fluid under consideration. Okay, so this is the case in which the fluids under consideration and from which you are measuring the pressures are having the pressures less than the atmospheric pressure, and these are the equations for the fluids for which the pressures are more than the atmospheric pressure. The atmospheric pressure is also called as barometric pressure. Barometric pressure is relating with the device barometer that is used to measure the pressure, and we will discuss about these devices to measure the pressures in the later slides, and varies with the in the coming slides, and varies with the altitudes. Also, at a given place, it varies slightly from time to time because of changes in meteorological conditions. If the meteorological conditions are going to be changed, then the atmospheric pressure is also going to be changed. Okay, so if this is the pressure of the fluid, that will remain constant, but in between this ordinate can move up and down. This atmospheric pressure is not a constant value, it is going to give you certain variations with the certain conditions. Mean if the meteorological conditions, the height with respect to the absolute 0 is going to be changed, then this atmospheric pressure is also going to be changed. Okay, so this ordinate can be move up and can be moved down. So for at a particular altitudes or the particular meteorological conditions, the atmospheric pressures will be different, and for those different values the pressure for the fluids under considerations may be different. So you must be very clear with these parameters at the time when we are measuring the pressure. So P atmospheric, here you can analyze or you can see a certain examples like P atmospheric at the sea levels at 15 degrees centigrade is 101.3 kilonewton per meter square. As we are going to be move up at the height above the sea levels, and if we are going to change the temperatures, then this P atmospheric will also be changed, and atmospheric pressure head is different. I told you, if you are the pressure head is a different terminology and pressure is different terminology. So pressure head is 760 millimeter of mercury or 10.33 meter of the water. Okay, so in this way, one value of the PE atmospheric and the atmospheric pressure head is given to you at a certain temperature and at a certain level. So if level is going to be changed or temperature is going to be changed, this value of the now, we will discuss here. We are only having a brief description about the measurement of the pressure, how we can measure it by using different devices, and the detail of the devices, how it works, their derivations, that we will discuss in detail in the second part of this chapter. So this is the last slide of this part 1, in which we are only going to be briefly discuss the introduction of the measurement of the pressure and the devices that we can use. So generally, the pressure of the fluid can be measured in two ways. First of all, by using the manometers, and secondly, by using the mechanical gauges. What manometers are? Manometers are defined as the devices used for measuring the pressure at a point in a fluid by balancing the column of the fluid by the same or another column of the fluid. They are classified as the simple manometers like piezometer, U-tube manometers, single column manometers, and the differential manometers like U-tube differential manometers and inverted U-tube differential manometers. Mechanical gauges are defined as the devices used for measuring the pressure by balancing the fluid columns by spring or the dead weight. The commonly used mechanical gauges are the diaphragm pressure gauge, the Bourdon tube pressure gauge, dead weight pressure gauge, and bellows pressure gauges. Okay, so in some type of the pressure gauges we are going to be discussed in under the heading of the mechanical gauges, and this manometer, all type of the manometers we will discuss in detail, the derivations, the working also. Okay, so this is it for the first part of your chapter, in which we have discussed, I am concluding all of the points that we have discussed about the pressure, hydrostatic pressure developed or generated for a certain fluid, and the pressure head developed for a certain fluid at a certain point with a certain height h or the z. Okay, the vertical height, and also the different type of the pressures generated or produced within the fluid, that may be the absolute pressure, the gauge pressures, and the vacuum pressures, negative pressures, and how those are going to be measured in terms of by using different devices like manometers and mechanical gauges, and the working of the manometers and the different type of the mechanical gauges we will discuss in part 2 of this chapter. And this is it for this part, and see you in the next part, and we will discuss in detail about those. Thank you so much, guys.